I'm Marissa.
I'm Kaylin.
And this is Teenage Science!
This is a vlog where we take science topics and make it more understandable for people our age. And today our topic is
Motion maps!
In particular with
Constant velocity.
And so that's what we're discussing today.
And for those of you who haven't seen our show before, we have this thing called Sci Dolls, and that is our science dolls, and they're always ready to learn science.
Woo! First thing we're gonna go over is what motion maps are and what they're used for. So motion maps are used to show the movement of an object along the distance it traveled. And it can be demonstrated on a straight line or a ramp.
This is the basis of a motion map. It shows 0 to 5 meters in the time interval of 0 to 4 seconds.
Make your origin clear, because like you can't just not put the 0, because the writer can, like, you can honestly start at any origin you want to. So our distance is going to be 0 to 5. And for a motion map, this is an important thing to remember, that you always put a dot, this one dot, the first dot that you have on your motion map represents 0 seconds. This is not, you don't just automatically start off with 1 second. This is a 0-second dot.
And that was one of the things that both of us pretty much had a problem with when we first started doing them. So yeah, make sure that you know that it starts with the 0.
So if you're like showcasing like 6 seconds of motion, you're gonna have 7 dots, because
you always have
one more
dot
than you're actually showcasing.
We have these dash marks on each arrow because those represent that they are all equal,
and that's what the
they're
main
representing
point
constant velocity.
So even if like you happen to draw one like a little longer than the other, you can draw the congruent marks to make sure that the person knows that you really want them to all be the same. When you have constant velocity, that means there's no acceleration because your velocity is remaining the same throughout. So as you notice, we don't have any acceleration vectors on this motion map because there's no acceleration. The direction the vector is pointing represents the direction the object is moving. So since this
is going positive, and we will show y'all how that graph would look later on in this
But
segment.
if we wanted to show it moving in the negative direction,
then the arrows
right that way. And then your origin would probably start over here, so you could show it moving towards 0. So it's like,
you can create a motion map from a position versus time graph, or from a velocity versus time graph, or even from a description. We're gonna have a little race, okay? We have runner A and we have runner B. Let's see how they work out. Well, first we're just gonna describe the graphs to y'all. So in this one, we see that runner A is going faster because the line is steeper.
The second one, runner A and runner B, the slopes are the same, so they're traveling at the same speed because the slopes are the same. They're just starting at different starting points. So B starts at 0 and then A starts at a point on the y-axis. So that's the only difference, but the slopes are the same, as you can see, because they're parallel. For this graph, A and B, the slopes are different. A looks a little steeper than B, A steeper than B, and they also have different starting points, but they intersect at this point. But A is steeper, and then A has a lower starting point than B. So B is moving at a faster velocity than A.
And now we're going to have a brief break to show y'all how to do selfies. Selfie!
So now we have examples of motion maps with constant velocity. The longer vector just shows that the velocity is greater for each, but all of the vectors for each of them have the congruent mark showing that they're the same though. Like one is just greater than the other, but it's constant velocity.
Runner A is starting at a higher position than runner B is, which is indicated on our motion map. See, runner B is starting at 0 meters, but we can see that A is going further than 0, starting further than 0, because remember that first dot is 0 seconds. And they are both going at the same velocity, and the velocity is constant. And that's your motion map.
We have A and B, and like I said before, A starts at 0 and B starts higher up on the y-axis, so it has a higher starting position than 0, but this is qualitative, so we don't have any numbers. And so
A is going in the positive direction, while B is going in the negative direction.
B is slowing
indicated
down.
on the motion map.
Yeah.
You see
But
it is
B
going to
also
negative,
has
positive.
all of the arrows are pointing this way, showing that they're moving in a negative direction. It is qualitative, but we did just put the numbers to kind of just showcase, like to make it clear, but this is qualitative, so there's no number. So 5 is not technically a real number represented in the data, but we're just putting that to showcase that
Another
it's moving
thing,
towards a greater
this may not even
distance.
be going to 0 meters because we don't have something indicating that we're stopping right here. This can go all the way to the negative region. So this would be wrong as well.
B has a larger, faster velocity, so they have a longer vector.
So today we have our special side doll of the week, and she is Test Drive. Woo! So we're gonna give her a problem to solve, and she's going to do it. So we encourage all of our side dolls out there to take a pause and solve the problem.
All of our examples, you should try to do it yourself.
So we have a position versus time graph where the object moves in the positive direction for 2 seconds, then in the negative direction for 2 seconds. We also included a velocity versus time graph just to give you a little introduction of what one looks like.
So I think I got it.
So let's see if Taj did the motion map right. We have the first dot at 0 seconds on the 0 meters. We have the first second at
2 meters,
2 meters.
because it's moving at 2 meters per second.
We have the second at 4 meters. We have the third second at 2 meters.
It's moving back.
And then we
towards
have
0.
the fourth second back to 0 meters. And it is going positive for the first 2 seconds, and then it's going negative for the last 2 seconds. You always have to remember to put your arrow on the last dot because it can continue to go in the negative direction.
And it's
Good job, and your prize is
I wonder what it's gonna be.
confetti ball.